Case duality. So in the case theory was ABAM, and we saw that this is a two-parameter theory, so we have these two parameters A and N. And then the first gravity dual that we had was M theory on ABS4 times S7 K. And this theory has, again, two parameters, K, which is purely geometric, and then the radius of ABS4 and S7 divided by the Planck length. And then we saw that the relationship was this form. And it's very interesting now to try to understand what is the moduli space of this theory. So you see that K here, I'm going to assume is fixed because it's a geometric parameter here. So essentially the only parameter you have in the gravity theory is actually LP over L. And then what happens in the gravity theory when LPLL is much smaller than 1, what you have is weak gravity. This is the large distances, so gravitons are weakly coupled. So this is where supergravity approximation is good. And conversely, we have a region where LPL is of bigger or of order 1, and this is actually when your universe is of Planck length. This is a Planckian universe. The radius of ABS4 and of S7 is of the order of Planck length, so this is a strong gravity, and this is where quantum gravity effects are very important. And this is also where you expect also the full force of M theory, the full ingredients of M theory to correctly dimensional supergravity. Now, since LP over L is proportion, LP over L to the 6 is proportional to 1 over M, we see that this regime, supergravity from the point of view of the gauge theory, is actually a gauge theory at strong coupling in the sense that K here, remember that K here is an integer, 1, 2, blah, 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 and our gauge coupling was essentially 1 over K. So if K is, so you see that if K is 1 or 2, etc., we are actually in the regime where the gauge theory is actually strongly coupled for small values of K. So gauge theory has finite coupling, let's say. And N is large, so supergravity is when N is large, and conversely, this is the regime where N is it's not a very, it's of order 1, say here. Okay? Now, a consequence of that is that the large distance expansions, so large distance expansion of supergravity, I mean an expansion in this parameter LP over L. Okay? So the expansion in this parameter is going to be a 1 over N expansion in gauge theory, but a fixed K. So this is not the top regime, because in the top regime you take N to infinity and K to infinity, so that N over K is 6. So I call this regime of the gauge theory the N theory expansion of gauge theory. And this is something that it's new with respect to ADS5, because here the reason why this expansion is possible is because you have an N theory dual on top of having a type 2 string theory, a type 2A dual. I will now discuss the type 2A dual, but this regime is very interesting and is different from the top regime. So this is the N theory expansion of the gauge theory. And this is more like a thermodynamic limit. It's a standard thermodynamic limit. It's just that your coupling is fixed, and you take N very large, and you make an expansion in 1 over N. So you want to actually see signatures of N theory from the gauge theory, you have to use this limit. Okay. Now, of course, we also want to recover the type 2, the top expansion of the gauge theory, and in order to do that, so we go to the other, we go from N theory to type 2A. So let me review here what happens with type 2A. I will state what is the dual, And then I will propose as an exercise to go from this background that also discussed in the morning to this type 2A background. But let's first say what is the type 2A background. So this is a background in 10 dimensions in which the 4-dimensional space is also ADS4, but now your compactification manifold is CP3, the complex projective space. The metric, it's again this form. So you have this a direct product of ADS4 metric. And now you have ds CP3, ds per CP3. And now what are the parameters of type 2A string theory? Well, you have a length scaling string theory, which is the string length, and then your adimensional parameters would be the radius of compactification divided by the string length. This is one parameter. And now there is no geometric parameter. Now in principle you have a coupling, which is the string coupling. And these are the two parameters that you want to understand. Actually, there is an important insight about these two parameters. And this is that you can think about this as an H-Planck constant in space-time, where this is an H-Planck constant in the worldsheet. So the reason to, I mean, if you don't remember this, remember that the string action, you usually write it like this. So you write it like d mu x a, d mu x beta, d alpha beta. And remember that alpha prime is ls squared. So this action is measuring the area of the string in units of this. So this goes like L squared over Ls squared, but an action should go like 1 over H bar. So you see that the worldsheet coupling, the H bar for the worldsheet theory is actually Ls over L to the square. Okay? And then you can think about GS as the strength of an interaction in space-time. So this is what I would call maybe you can call H bar of space-time. So this is a two-parameter theory. Now the dictionary, you can actually derive it from here, as I will propose now this as an exercise. The dictionary between these two parameters here and the Kn parameters of the gauge theory is the following. You have L over Ls to the fourth. This is very similar, it's a little bit similar to what is there. Is 32 pi squared. Lambda, where lambda is the top parameter of the gauge theory. And, very important, G string. Can you see here? They're right here? Yes? No? Not really? Okay. Right. Let me just write this and then. G string is actually 1 over K L over Ls. So this is proportional to Gs minus lambda to the 1/4, or it's also proportional to numerical factors to 1 over n lambda to the 5/4. So this means here, this is a very important equation. This means that since in this limit lambda is fixed, doing an expansion in the string coupling constant is doing an expansion in the coupling constant of the gauge theory, or doing an expansion in 1 over n. Okay? So the string coupling constant expansion is the 1 over n expansion of the gauge theory in the top limit. Okay? So let me put this there, and actually maybe here I can add this exercise here. So exercise, derive this dictionary for type 2A theory, derive the type 2A dictionary from N theory. And for doing that, what you have to do is to do the kind of vibration that we saw in the morning, a different context, in the context of three-dimensional theory. You have to realize that S7 is a vibration over CP3. So you can now use S1 as your M theory circle. This is a non-trivial vibration, so there will be, for example, a non-trivial Ramon-Ramon one-form connection. But using this standard construction, this is this Hopf vibration, you can actually derive these relations here from this single relation here. Okay? Now, again, the interesting thing is to understand what is going on in the type 2A dictionary as compared to the string theory. So now we have a two-parameter space. So let's write here a two-parameter space. So let me call here lambda. I will write this lambda parameter there. Where I have my abilities. And lambda, remember lambda is like lambda over is L over Ls to the fourth. So this means that it's like 1 over h equals to the square. So this is a small lambda, this region is a small lambda, this region is large lambda, and here, so let me write here the gauge theory parameters. So here we have, say, 1 over n for the 1 over n expansion, and here we can actually use the string. So this is the type 2A theory. So this region here, which is a small lambda and large n, okay, this is a small lambda large n. This is planar perturbation theory in the gauge theory. Now, when lambda is large, you see that h bar is small. So the action of the string is actually not very. I mean, the quantum theory of the worldsheet is not very quantum because h bar is very small. Okay. So sorry, I don't say it. Okay. Yes, h bar is very small. So the h bar corrections are small, and here you can actually use the supergravity approximation. And now if you turn, so you see that the easy part of the gauge theory, which is perturbation theory, is the hard part of the string theory, and the other way around. So again, we have here the typical interpolating problem that we were formulating in the morning, but in the language of string theory. So if we do a supergravity calculation here, we will be able to get a strong coupling behavior of the gauge theory, but it will be very hard to test from the perturbation theory and the other way around. And now, if you increase the string, here, this region here is the planar theory, because as I mentioned there, you can see from this dictionary, you can see that the FG that we were discussing this morning in terms of the gauge theory is related to a string partition function of genus G. This is up to numerical factors. This is just an overall power of lambda, FG gauge. So you see that if you actually compute this free energy of genus G at fixed lambda, you actually get the free energy of the genus G type 2A string at fixed lambda. Okay? So the genus expansion is actually the 1 over n expansion. But this is again different from the n field expansion that I was mentioning there. And if you are here in the middle, it's a mess. Here, for example, you have how would I put it here? You will have quantum corrections in the worldsheet. Even at genus 0, you will have quantum corrections in H bar worldsheet. So, for example, one could have here worldsheet instantons of the form e to the minus 1 over H worldsheet. These are, we actually will see that they are effects like this, which are exponentially suppressed and non-perturbative. And if you are here when G string is big, then you have here, really surface of higher genus, which actually fluctuates. So this is the wild region where you have, strings of arbitrary genus. The genus is non-suppressed if G string is large, and then you are also have to take into account corrections coming from fluctuations of a string of fixed genus. So you see that this is a very complicated parameter space. It's a two modulus parameter. It's a two moduli space, and in principle, when you are in the middle, you have a very complicated situation, both from string theory and from the point of view of this theory. Okay, so this is kind of more or less the general picture, and now what I want to do is to tell you a little bit how one can actually do calculations in this regime and in this regime in order to see what are the two streams that we want to join eventually by an interpolating function. So we mentioned here all these ADS-CFT correspondence. We made a dictionary. I explained to you what is the dictionary of the parameters, but now we want a dictionary to calculate things. And actually what I'm going to use is the simplest version of this dictionary, because what I want to calculate is the partition function of the three-dimensional theory. So what is ADS-CFT telling me about this? Well, actually this was one of the proposals that Witten put forward in his famous article in 98, that ADS-CFT should imply an equality of partition functions. This has not been very much used until now, but it's actually the simplest statement you can make, in a sense, in ADS-CFT. There is no complication about a map between operators on both sides. This is just a partition function. They should be just equal. They are just functions. So here I'm going to think about the partition function of a manifold M. Eventually we will want to discuss, say, an sphere in dimensions, and these are the parameters N and K. I'm writing here sometimes things in a little bit more general, because you can actually write this more generally, but I'm thinking all the time in AVN theory. So if you think that I'm not being general enough, it's because I'm focusing on AVN theory. So this should be just equal to what? To the partition function of a string theory or of M theory, depending on which kind of point of view you want to adopt, in the corresponding ADS for a space. So here we have, again, and maybe you could say x6 or x7, depending if you use the string theory and M theory point of view. And the most important thing is that the boundary of ADS4 should be the manifold M that you are interested in looking at. Okay. So this, and everything is Euclidean. Right? Again, I'm using the Euclidean version of ADS4. So this is a statement. Of course, both sides are hard. In particular, sometimes people say that you actually use this thing to define this thing, but at least you should. There are some expectations about this thing that should be true in any definition of string theory and theory. Namely, we expect that the M theory partition function on ADS4 and the 7 in the supergravity approximation, so this is the supergravity approximation, should be equal to the exponential of what is the partition function. Well, it's just the axiom evaluated on the solution of the equation of motion, so the axiom evaluated on shell. And this is just if I use the standard point of view in which I have a theory of ADS4 coming from Kaluza-Klein relation here, I just should get this thing. Just the Einstein-Hilbert axiom, together with a cosmological constant, because we are in ADS4. And then, if I'm completely correct, I should have here some Gibbons-Hawking term, because I'm working in a space with boundary, right? So there will be a boundary of this space, so I should add a Gibbons-Hawking term. Okay. So this is the expectation we have. And this is something that should be equal. Since we are in supergravity, we know that supergravity is, as I was explaining here, supergravity here is large n in the gauge theory. This is the kind of quantity that I should be able to compute in the gauge theory at large n. So if you are using the M theory point of view, I will actually rely more on the M theory point of view in these lectures. You are thinking about the M theory point of view, this will be equal to the partition function of the gauge theory at fixed k and very large n. So you should take some sort of thermodynamic limit of your gauge theory at intermediate or strong coupling and calculate it. Now this is hard, but this is easy. So how can you calculate this? Well, the calculation of this is really very elementary thing, but there are some subtleties. So I'm going to use a cheap way to calculate this. I'm not going to use the expensive way. The expensive way takes just more time, and the results are the same. I'm going to present you the cheap way. Then you won't be convinced, and then I will refer you to the more detailed literature on this. Okay? But it's really nice because it's an easy calculation that one can do. And actually, this is the way we did it the first time was the naive way, and it worked. So then we realized that there was a more expensive way of doing it. but for pedagogical purposes, I'm just going to show you what is the cheap way. Now, the cheap way is actually very instructive because there are phenomena you see in this kind of easy calculation that you don't see in ABS 5. So this is again something that. So let's see. So we have to calculate then the Einstein-Hill reaction in ABS 4. In ABS 4, which has this boundary. So what we have to do is we have to choose an ABS 4 whose boundary, say, is Sn or S3. Now, this actually was already in the original paper by Witten. So you need an Euclidean ABS metric whose boundary at infinity it's an SN sphere. And this is actually easy to find. So this is this metric there. So there are many possible ways of parameterizing, but I will use this one. So what we have here is we have a coordinate rho, which is the radial coordinate, and at infinity you have this metric on Sn. So this is actually the appropriate metric. So here you have an Sn. This is the metric on Sn with this factor here. So this is the standard metric that you should use to compute things on Sn if you want to use ABS CFT. Now, so let's now calculate the Einstein-Hill reaction evaluated from this. Now, if you use the equations of motion, so this is a metric of constant curvature. So this is what you get, lambda over n minus 1 mu. So this is the equation of motion. Then you see that on shell, the Einstein-Hill reaction is just proportional to the volume of ABS 4. This is n here I'm using ABS n plus 1 with boundary Sn. I'm just being a little bit more general. Then I will specialize to L equal 3. So the Einstein-Hill reaction, this is a trivial exercise in general relativity, or is just given by an overall factor times the volume of I just use G small g. Okay. So this is just the volume of ABS 4. Now it's very easy to see that this is a divergent thing. The volume of ABS 4 diverges as you go to infinity. You see that immediately that this diverges. So we have a problem here, but let's anyway use the naive way in which we regulate the values. Let's put a cutoff and see what happens. Okay. So a cutoff means that here, instead of integrating from rho to 0 to infinity, you just put a cutoff here, say at rho naught. Okay, so let's introduce a cutoff. Rho naught, and let's see what happens. Well, if you compute this, what you find, so this is the volume, what you find is an overall factor of, let me do it for n equals 3. You get a factor n equal, you get, the dimension full factor. Then you get the volume of the boundary, the volume of an S3 with radius 1, and then you get the integral from 0 to rho naught of dou d rho change of rho to the cube. And this is the kind of factor that if you take rho naught to infinity gives you a divergence. This is the source of the divergence. So let me continue the calculation here.
Marcus, what are you computing now?
I'm just computing the Einstein-Hill reaction evaluated on this metric. Okay, just that.
I see, because I thought the bulk term when you evaluate with the equations of motion is 0, and then the Gibbons-Hodgkin gives a non-zero contribution.
No. This is what happens, say, for the Schwarzschild-Blackwell and so on, but not here in this example.
I see.
It's slightly different. That's part of the interesting thing of this calculation. No, actually, of course, on your face this is divergent already. It's not 0, it's divergent. Now the question is how you regulate this. Now, if you do this integral, okay, this is an elementary exercise, and it's good to do elementary from time to time. So let me just look at this integral. If you look at this integral, and you get 1 over 12 cos of 3 rho naught minus 3/4 of cos rho naught plus 2/3. So So the amazing thing about this is that there are two pieces that diverge exponentially, but there is a finite piece. Okay. Now, it turns out that the right prescription to regulate this thing is to put this to 0, and to keep the finite piece. This is the cheap way of doing it. Now, okay, now let me just tell you what you get at the end. At the end of the day, when you put everything together, you get the Einstein reduction. When you put all this together, gives you pi L squared over 2gn. And if you did the exercise I proposed you in the morning, what is gn, you get this expression here, which is the prediction of the famous n to the 3/2 behavior of the n to the race. So, is this, now here I have been very cheap. So I just picked the finite piece of the bulk action. I completely forgot about the Gibbons-Hawking term, etc. Well, it turns out that there is a serious procedure to do this, which is called holographic renormalization. So in holographic renormalization, what you do is you introduce a set of universal counterterms, and this is very important. These counterterms are universal. They are the same for ADS4 and for ADS5, for example. Now, if you go to ADS7, you have to add another counterterm. For ADS4 and ADS5, they are the same, they are universal. And these terms will actually work out in the context of ADS5 to check, to get actually finite, because you find the same problem in ADS5 to actually regularize infinities. Now, in ADS5, you don't get a finite piece here for the bulk action. But what you can do is just use this procedure of holographic normalization. So this means that you have to add here counter terms. And if you use these universal counter terms, and this is very important, these are universal, they are not chosen ad hoc, they are chosen in such a way that, for example, you get the right Casimir energy for n equal 4 super-Young meals, they are chosen in such a way that you get the right masses for black holes at asymptotic infinity when you calculate the stress energy momentum tensor, etc. You use these universal counter terms, you see that the Gibbons-Hawking term is also divergent, that is cancelled, all these things is cancelled, and then the finite piece is the only thing that survives. So this was actually done by Baran, Johnson, and Myers. I think in 99 or already it's a while ago. So this cheap thing gets indicated by this more complicated thing. So the more complicated thing takes much more time. Okay.
In 4 dimensions is equivalent to subtracting a reference.
Well, in 5 dimensions, the problem is that you have a logarithmic reference.
No, but I'm saying in 4. I mean,
in 4 dimensions, yeah, in 4 dimensions it means that exactly you actually get.
Because usually you subtract the reference frame.
Yeah, but this is different.
That's another way of.
But the problem is that in ADS, in holographic normalization, you have a more intrinsic way of subtracting the divergences. So there is no reference metric. Is what you do is you have local counterterms on the boundary. Okay, this is the different thing. So it's a different kind of prescription than the one that Gibbons and Hawking originally introduced.
Okay. Can you get the same thing by analytically continuing?
Yeah, actually, that's a very good thing. There is actually an alternative procedure which is used dimension, epsilon regularization, and then you regulate the volume. And this has been studied by mathematicians. For example, there is a paper studying. It's by Dorn, I think it's Dorn, where they explain this kind of procedure of volume regularization using epsilon prescription, and again you get the same results. All these results get to the same. So this is really using dimension regularization and removing the 1 over epsilon pole. So it's the same. So this is the result that we should be able to match. Okay. Good. Okay. So now, so this is the strong coupling prediction, and now this is what we should find here. But what we can try to do is to do a calculation in the gauge theory with coupling to see if this function is going to be trivial or not. Sometimes in ADS CFT you find that the strong coupling prediction is the weak coupling prediction. The best example in this kind of circle of ideas is the Casimir energy of n equal 4 on S3 times R. There you do this kind of calculation and you get a number which is actually the same one that you get a weak coupling. And this is because there is a non-renormalization theory that protects this quantity. Now, the first thing we have to do now is, okay, maybe a weak coupling we get the same. But this is not going to be the case. Okay, so here we must have a non-trivial interpolating mass. So let's sketch the calculation of weak coupling, because it's again a very nice calculation. a really kind of very nice quantum field theory calculation. So we take ABM theory here, and we do this weak coupling calculation. So a weak coupling, what you have in a quantum field theorem curve manifold, what you have is just a bunch of fields with differential operators which couple to the curvature, and the only thing you have to do is to evaluate this. To evaluate a one-loop determinant is to evaluate a functional, a one-loop calculation in a weak coupling. It's a free field theory calculation. So we want to do a weak coupling. So a weak coupling is schematically what you have. So what you have in ABM theory? Okay, you have the supersymmetric Chern-Simons theory, and then we will have the matter theory. And after you integrate all these auxiliary fields, what you actually get is you get two gauge connections, then you get a complex scalar, and then you get these two fermions. And these are, remember, there are 4 of these in the bifundamental, so there are 4 of these in the bifundamental. And the action schematically is the action of the free theory, right? So you have A1 wedge dA1 plus A2 wedge dA2 plus, minus 5 d squared 5 plus I plus gamma I. So here you have four operators, and the partition function of this theory one loop is just a bunch of determinants. So we have here the determinants of A1 and A2. So let me call this the determinant of this operator here, R1/2, the determinant. I'm writing this in, let me call this the operator for the 1 and this operator for the 2. The operator for the second gauge field, and then you have the determinant of the Laplacian of this guy for a complex scalar. So since there are 2 scalars, I just have this. And then here you have the determinant for this guy, which is the determinant of the Dirac operator. So this is the action at one loop. This is a very trivial calculation. It's just a bunch of functional determinants. Now it's very important that we are working on S3, because on S3, these determinants have a discrete spectrum, and then you can try to regularize these determinants and calculate them. So you can actually use, if you are doing quantum field theory on curved space and you want to calculate determinants, there's a very beautiful technique which was introduced by Docker and Critchley and also by Hawking, which is called zeta function regularization. And this is a kind of textbook example of zeta function regularization. You have some scalar spinors and let's say exotic vector fields propagating on the sphere. I say exotic because the kinetic term here is not the standard one. It's the kinetic term, it's a first linear, it's a first order limit of the differential operator, it's a second order differential operator. But in principle, you can also deal with that. So you have to use zeta function regularization, and you calculate this thing. And the details of this calculation are spelled out in exhaustive detail in my lectures. And it's a really nice exercise in quantum field theory in curved space. It's actually an easy exercise. And then I'm just going to present you the result. Maybe I should comment here that here I have been a little bit fast, because since we want the theory to be conformal invariant, we have to have a coupling to the curvature. So a scalar field, in order to have a conformal invariant action on a curved space, it has to be coupled. The coupling to gravity cannot be the minimal coupling. It has to be what is called the conformal coupling. So it gets an effective mass here. Okay. So this is actually what is called sometimes the conformal Laplacian. It's not the standard Laplacian. This is also of course, it's very important to get the right result. Okay. But this is a standard thing for these CFTs in curved space. Okay, so what do you get when you do this calculation? Well, now the matter theory, let me write it like this, C1 loop matter. So the matter part is by far the easier one, the easiest one. Okay, so you have to calculate this. This is the matter part. You have the conformally coupled scalar and the fermion. And let me assume that actually I can write an expression for any representation. So if these guys are in the representation R of the gauge group, the result is just this. So dr is the dimension of the representation. And for the Chern-Simons part, things are a little bit more complicated. And again, in my lectures you can find a detailed discussion, but it's a very subtle calculation because you have to do gauge fixing. It's a code calculation you have to do, taking into account, being very careful with the overall factors and so on. And there is a shortcut. If you want to calculate just the Chern-Simons part, on S3 there is a shortcut, which is you go to the paper by Witten, in which he wrote the exact expression for the partition function of Chern-Simons theory on S3, and you just take the weak coupling limit of this expression. Okay, this is much faster. What you get is that at one loop, again, let me at one loop, you get n squared over 2 log of 2 pi lambda minus 3/2. This is what I was mentioning this morning. You see here you have n squared, so this is here I'm actually restricting myself to the planar part, so the thing that goes like n squared. And notice that there is a log lambda, so this is not analytical lambda equals 0. But this just comes, this is just a one loop part. So this it doesn't have to be necessarily analytical lambda equals 0. Starting from two loops, you must be analytic, okay? But there is an analytic part here. Now when everything gets, so now we can, this is just a single Chern-Simons factor. Now in ABN theory, what we have is what? Well, dr, you can think about this as 4n squared. Because we have bifundamentals, so there are n squared of them, and there are 4 of them. And then we have two Chern-Simons vectors. So when everything is added, what you get is this expression, which is order n squared, and then you have log of 2 pi lambda minus 3/2. So all this comes from the Chern-Simons thing because we have 2, and then you have to take into account this guy here, so we have 2 log 2. So this is the free energy on the 3 sphere of ABN theory. So it's a very easy calculation. You know, when I was first giving seminars on this partition function on the 3 sphere, people were really very, you know, what is this quantity? It's not the thermal free energy. What is it? Blah blah blah. Well, you know, if you have free fields, this is very easy. It's just this quotient of determinant, right? And you take a determinant of the appropriate field. You calculate its eigenvalues for the corresponding operator, and then you can calculate this using set of function factorization. So here is my weak coupling result. And here I have my strong coupling result. So if I take the log of this, let me just put it this way. Yes, then I have log. So let me call this lambda small, and this is at lambda large. And actually, I don't want to write it this way. Well, I want to write it in 2 ways. This is one of them. But then what I can do now here is use my definition of what is n and k. So you see that this is minus chi square root of 2 over 3, 1 over the square root of lambda. So you see this is the main story here. The weak coupling result, see this is for lambda much bigger than 1. So you see the weak coupling result goes like log of lambda, and the strong coupling result goes like 1 over the square root of lambda. So they are not equal at all. This means that there must be a function. All this is the planar, it's a planar quantity. So there must be a function f0 of lambda, which at weak coupling goes like this, and a strong coupling goes like that. And your task now is to find this function in the gauge theory, calculate it, and show that actually when lambda is bigger than 1, you have to recover this thing. So you have to resum all these diagrams. So this is just the first step of the calculation. This is just the one loop now. There come all the loops. You have to do the calculation and resum it. Do the anti-continuation at lambda bigger than 1 and obtain this, which is a very daunting task. So that is in principle what you have to do. Okay? So this is essentially everything you can do with the standard techniques, and now you have to think about something more clever in order to be able to make progress on this. Now, again, notice that here at fixed k we have an n to the 3/2 behavior, while here we have an n squared behavior. So you can think about this in two ways. You can think about this as, at fixed k, this goes from n to the 3/2 to n squared log of n, or you can think that in the planar limit you have a function which goes from log of lambda to 1 over square root of lambda. These are equivalent ways. So this is the kind of problem in which you have very different behavior at strong coupling and weak coupling, and this should come from resumming an infinite number of diagrams. Okay, so now in order to make progress and being able to connect these things to a single function, what we have to do is to use this method of localization, which Johan was introducing in his talk this morning. Okay? So I will introduce now the method of localization, see how far I can get, and then what I will do, I will eventually obtain a matrix integral, and then what I will do tomorrow is I'm going to actually calculate this matrix integral for you at large n, and I will get exactly this result with exactly this coefficient. Okay? So I will finally prove this. Okay?
But for localization, you don't have to assume large n.
Sorry? No, I don't have to. That's why my lectures were called localization at large n, not just localization. I will do that, but of course you can do finite n. But the question with localization, once you have this expression, extracting the large n limit of this expression is also non-trivial. I mean, it's of course much easier than extracting it from the full gauge theory, but this is still non-trivial. And this is what I'm going to do tomorrow. So maybe this is a good point for asking questions, comments. Okay, so let's start thinking about localization. And so the essential idea of localization was introduced already by Johan this morning. So what happens with localization? Well, so the setting for localization is the following. So imagine I have a theory with an axiom, S of phi, where phi is the set of all fields of the theory, and you also have a Grassmann symmetry in the theory. Symmetry delta, and the fact of being a symmetry means that the action has to be invariant under this symmetry. Okay. So, for example, acting on the Lagrangian, this could induce, for example, boundary terms, but after integrating and assuming good behavior of the fields at infinity, this would be zero at the end of the day. Now, this action in general squares, as again Johan was explaining today. Should square to a symmetry of the theory. Okay? So this symmetry could be, for example, a gauge symmetry, or actually what you can check in this supersymmetry distribution of matter theory is that this squares to a gauge symmetry plus a dilatation plus other symmetries of the theory plus a Lorentz rotation. So the question is that it has to square two symmetries. Okay. Okay, so these are the only ingredients I need. So I will try to be pretty general here. So now imagine that you want to calculate the partition function of the theory. the integral of all the fields of image of sky. And now what we are going to do is we are going to perturb this quantity by introducing a uniparametric dependence. And we are going to perturb this theory with D acting on V. So V is going to be a Grassmannian quantity. It can be a Grassmannian combination of the fields. And we assume that D square of V is LV of V is 0. So V has to be invariant under the symmetries of the theory. It has to be, for example, if this is against symmetry and Lorentz symmetry, it has to be against invariant and Lorentz invariant. It's not a big requirement. Okay. Now imagine that you have this. Now imagine that you want to see how this varies with respect to t. So if I take a derivative with respect to t here, what I get is I put this down in the integral. But if d is a symmetry of the action and d squared is 0, I can write this as a total derivative, right? Because it's a Grassmann symmetry, so it has as a derivative. So dv is what we have, and d acting on all this is going to be 0 by my assumptions. My assumption here and my assumption here. So formally, I can now integrate by parts. This is, if you want, this means that I'm integrating a variation under asymmetry in the theory, so this would be 0 if the fields behave sufficiently well at infinity. This is not always the case. There are examples in which you cannot do this integration by parts. This is like integrating a total derivative. A total derivative gives you 0 if everything goes well at infinity. But there are cases in which it doesn't. After you take topological field theory for dimensions in certain type of manifolds, this is not true. So this is a formal argument. This is a formal argument. And every time you use it, you have to be careful. Okay? But here apparently it works. Okay. Now, since this doesn't depend on t, I can calculate everywhere I want. I can calculate at any value of t I want. So of course, if I calculate this at t equals 0, I recover my original theory, right? So z of 0 is what I want to calculate. This is the partition function of my theory, of the original theory. But now, imagine now that I take t to infinity, and imagine that the bosonic part of this guy, so remember, V is Grassmannian, delta is Grassmannian, so this is a Grassmann even quantity. And it will have generically a bosonic part. So imagine that this part is 0 on a submanifold of field space. Now, you see that, and I also want this guy to be positive definite in general, okay? So you see that if I calculate this, the limit when t goes to infinity of z of t, every field which is not in this locus is going to be suppressed very largely in the integral, okay? So morally, and I write here this, let me call this some manifold homology space M. Morally, I should expect this integral not to be an integral over the original field space, but an integral over this sub-manifold of field space. I'm writing this, I'm not making this very precise for the moment mean, because now the analysis of this equality depends a little bit on the details of the theory. Okay?
Marcus, do you want to remove the V from the second statement?
Sorry, what is the V?
I think that delta V should be positive definite everywhere. Not just on the subnet.
Yeah. That's. I didn't say that this wasn't the subnet. I just said that this is positive definite.
No, but you want to remove the subscript B.
Oh, no. No.
Because you've set it equal to 0. So it's
No, sorry, you are not, you are not seeing. What I mean is that the bosonic part has to be positive definite as a functional on the fields everywhere. Okay, now, this functional will have some zeros. And let me call the place where this is 0 as a manifold model space. So for example, this thing in Euclidean space, right? This thing is positive definite. But it's only 0 when it is a constant.
Okay.
So this I need in order for this, actually, this I need in order for this guy to be completely dampening. If there was a region in moduli space where this is not consistently dampened, I could get something funny, right? I could get some reasonable space, but it's actually taking t to infinity actually makes the action growing. So what I want is, that this is positive definite only with the exception of some field configurations where it's actually vanishing. Okay, but I want this to be positive definite everywhere, and just the bosonic part, because the Grassmann variables I don't care. Grassmann variables do not have convergence problems. Where I need this to be well defined is in the bosonic part. Okay, so this is the typical thing. This thing is positive definite with Euclidean signature, but it's going to be say it's going to be 0 when this is covariantly constant. Okay, or well, in our cases it's going to be just constant. This is the kind of thing I have in mind. Okay. So it's now a little bit clear, maybe?
Oh yeah, no, I just thought B was referring to the submanifold.
No, B refers to the bosonic part, to the part which involves the bosonic fields. Yeah? I mean the bosonic, this is Grassmann even. What I mean is the part which involves the bosonic fields, because the bosonic fields are the ones that can give me, when I'm integrating from minus infinity to infinity. So let me, okay, so this is what I want. So I have to compute this, and in principle, my computation can be done in a smaller submanifold of field space. Now, if I'm clever enough, and this submanifold is very small, then I'm done. Because imagine, for example, that the only fields that make this vanish are constant fields. Then it's amazing because I have reduced a path integral to an ordinary integral. If all fluctuations of the fields are punished by this guy, and only constant configurations of the 5 fields contribute, then I reduce the path integral to a finite integral, to a conventional integral. And this is actually what is going to happen in these cases. So you reduce the path integral eventually. As we will see, M is essentially a configuration where only constant fields contribute, and then I will reduce everything to a finite integral. So this is the best it can happen to you when you are doing a functional integral. Just reduce it radically to a finite dimensional integral. Okay? So I still have 5 minutes, so maybe I'm going just to introduce the main actors for ABM theory, just making this general statement concrete for ABM theory. Okay? So let's see what happens then in ABM theory with respect to these things. Now what I have to do is to put the ABM theory on a 3 sphere, and it's not very hard to realize that this Grassmann symmetry is going to be a supersymmetry of the theory on the 3 sphere. Okay? So it turns out that in general, Euclidean Chern-Simons matter theories have actually 2 supersymmetries generically on S3. Let me call them B epsilon and B epsilon bar. And these are essentially the promotion of the standard supersymmetries of these theories to Euclidean S3. You can always extend supersymmetry for Chern-Simons matter theories. You can extend it from R3 to S3 in Euclidean signature, and then you get these two. So this is essentially supersymmetry on curved space. And now what you can see is that both of them square to 0, so I can take, for example, one of them. The anticommutator is non-zero, but it's a symmetry of the theory. It's a combination of gates, Lorentz, and so on. And again, if you want to see the detail, this can be worked out in detail. It's not my favorite job, but it's written down in my lecture, so you can check there that everything works and everything is like this. So we can just take one of them. As I said, this is non-zero, but each of them by itself squares to 0. So let's use this as our delta. Okay, let's use this supersymmetry generator as our delta. So we have already our delta. S, of course, the axiom of Chern-Simons matter theories is of course invariant under this supersymmetry. This is what we mean by having a supersymmetric theory. Now, what do we use for V? What do we use for V and for dV? Well, now, that's the question now. What do we want for V? Well, we want something that satisfies these properties. And remember, this morning, I was writing the Yang-Mills Lagrangian. And the Yang-Mills Lagrangian in Euclidean space had as a bosonic part 1/4 of m mu plus d mu phi d mu phi plus d plus sigma r to the square. So this is the bosonic part. So imagine that I would like to have this as dV bosonic, because this is positive definite in Euclidean space. Okay? Now, isn't this true? Can I write the Yang-Mills Lagrangian as d epsilon of something? It's actually true. So the Yang-Mills, super Yang-Mills axiom in 3 dimensions can be written as the epsilon of some d. This is actually not very difficult if you think in terms of superspace. If you like to think in terms of superspace, when you integrate these theta's that appear in superspace, each integral of theta is like acting with a covariant, with a super derivative. So you can think about you are able to write your Lagrangian, typically, you are able to write your Lagrangian as integral of d theta of something. This means that your Lagrangian will be delta of something for a supersymmetry transformation. Okay? This is not the case for super Chern-Simons theory, but this is the case for Yang-Mills theory. So what I want to do then is to consider, now I'm going to do first just the theory with just Chern-Simons, and then I will sketch you how you do with matter. So let me first do super Chern-Simons. So now I want to consider a theory, so I'm not going to consider matter for the moment. I want to consider a theory whose axiom is super Chern-Simons theory plus T of super Yang-Mills theory in 3 dimensions. Okay? So this is my new axiom. So I now want to compute the path integral over all these fields of my original goal, which was super Chern-Simons plus the super Yang-Mills theory. Okay? And now I can use this principle there. I can use this principle that I have here. Let me just... I know that this integral, should be able to do it by restricting to the submanifold moduli space where the bosonic part is 0. But where is this bosonic part 0? Well, since this is positive definite, in order for this guy to be 0, every single possible term has to be 0. Okay? So I must have f mu equals 0 by its own, d mu phi equals 0 by its own, and d plus sigma over r equals 0 on its own. Okay? But what is the solution of f mu equals 0? If you are in a generic space, f mu equals 0 doesn't mean that A is equal to 0. It means that A is a flat connection. Okay? But, so for example, you are doing Chern-Simons theory on cipher manifolds, there are many, as Johan was doing this morning, there are many flat connections. But on S3, since S3 is topologically trivial, there is one single flat connection. So here we are, A has to be equal to 0. So this is, already we killed a full field in this story. Because this manifold of field space is just a point from the point of view of the gauge connection. We killed the full gauge connection. Now here, the covariant derivative acting on phi, well, we have to evaluate it on where, we have to solve these 3 equations simultaneously. So A is 0, D of phi is 0, but, this is just D of phi, so phi has to be a constant. Okay? And, this is sigma. I'm writing phi, but this is the scalar. I'm just mixing the notation with the scalar. This is sigma. Okay. Sorry. sigma has to be 0. Sigma has to be a constant. And here we see that D, the auxiliary field, is to be this constant divided by R. So we see that we already achieved an important piece of our goal, and I will finish here. Out of all these bosonic fields, they are all dead, and the only thing that survives is an integral over a single constant field in the algebraic representation. And an integral over a field in the algebraic representation is sometimes called a matrix model. So we reach the conclusion already here that if this localization method works, we should be able to calculate the full partition function theory of the full partition function of Chern-Simons supersymmetric Chern-Simons theory as a matrix integral over this single variable sigma. Okay? So I will stop here, and tomorrow I will finish this story. But you see already that I have essentially completely simplified my life to a finite dimensional integral. Okay? Thank you. Yes?
Maybe you mentioned it, but if you take the t to infinity limit,
yes.
What does it tell you about the partition function of the original theory? So what is the relation?
Oh, they are the same, right?
They are the same.
Yeah. Because, you see, the variation with respect to t is 0. So I can take any value of t I want, you see. So z is constant as a function of t, right? So the valuation here and the valuation here should be the same. So that's why I'm doing all this story, right? Because at the end of the day, this simple calculation should give me the set of the original theory. Yes?
When you compute, what happened to the other specificities of ABJ? Because this is quite uncommon, right? So
yes.
you did not notice that you're in a free sphere or in flat space, or does it not? So are the other supersymmetries still there?
Which other solutions?
The other supersymmetries.
Yeah, but I mean there are two supersymmetries there in general for supersymmetry Chern-Simons matter, but you know, just having one.
You still have the full set.
Yeah. You have if you go to S3, I don't know if you can enhance the supersymmetry because of the fact that this is correct. You cannot.
You cannot.
Maybe you cannot. But you always have these two guys. Actually, I have to say that you need now here this epsilon is going to be a covariantly constant spin of S3. So you're going to have two essentially. Okay. So you have to choose a covariantly constant spinor. Now that you're on a Corpus space, you know, your epsilon is not a constant spinor, but it's a covariantly constant spinor, so you have to find for these ones. So usually you will have at least two, but one is enough. If you have one, it's already, it's like if you have, as long as you have the requirement of localization only needs one. Now, of course, sometimes you have a choice. You have many possible localizations. And typically it's the case that there is one choice which makes life simpler. So this, for example, mathematicians know very well this because they use this method to calculate some quantities. And sometimes you have many possible actions, many possible supersymmetries in quotation marks. But some of them, for example, have a complicated fixed point set. The point where the set where this vanishes is complicated. For example, you could have you could have an action in which you don't really reduce these guys to constants. You still have to do a path integral. So this is going to be still the same partition function, but life will be harder. So usually you choose the localization that makes your fixed point set M as simple as possible.
What would happen if I just tried to do, what would happen if I just tried to do the Super-Yang mills without the Chern-Simons? Is that well defined? Do I just get one for the partition?
Well, yeah, there is here one subtlety, and it is that let's put it this way: if you have if you want to calculate this, you cannot just put t to 0, right? This is forbidden actually. So essentially, for example, all the kinetic terms you must still have.
No, but I wanted to put the coefficient in front of the Chern-Simons term to 0 and get rid of that term.
Yes, I mean you want just to calculate the Super-Yang means partition function with localization, right?
Yes. Is that
right?
Would I get one for that answer?
No. You don't get one. The question here is that you have to be more careful because if you start with a t. So I actually thought about that. So actually with the matter theory is actually what happens. So in the matter theory, what happens is that the localization integral is the matter theory itself. Okay? So you can have a t. and then interpolate it between t equal 1 and t equal infinity. But you cannot put t equal 0, because then you get a divergence in the measure, right? You are having a Gaussian integral, and you are just removing your damping factor. So you cannot just put t equals 0 in the super-Yang-Mills theory. Right? You cannot say that the partition function is 1. It's actually infinity.
No, I don't want to put t to 0. I want to put the Chern. Suppose I didn't have Chern-Simons.
Yeah, you want to put k to 0.
Yes.
Okay.
I think localization here works, but your finite dimension integrals is not well defined. So you
Yeah.
get a matrix
I mean,
model without
essentially-
sigma square, right?
Essentially, I mean, yeah, there's, I mean, when you do the matter thing, you have t of the matter and say, okay, let's put the theory with matter, so adding matter to the theory is irrelevant. That is not true. Adding matter to the theory is irrelevant. The matter part of Chern-Simon's theory is actually delta of something. But you cannot put it to 0, because otherwise you get an infinity. It's a singular point of the theory. Now, if you want to put k equals 0, what you get? I think you also get a divergence coming from the you get a divergence coming from here, right? I mean, you have a divergence in the volume of the space, right? You are doing a Gaussian, and you are trying to evaluate the Gaussian when k is equal to 0, right? And then, when the constant is equal to 0, so you get an infinity.
Well, it seems sort of confusing, because I would have thought just ordinary three-dimensional Yang-Mills would be a reasonable theory.
But it's a reasonable
Yeah,
theory,
it's
but
reasonable.
localization doesn't give you well-defined theory.
Yeah,
There are many examples.
Okay.
of
Yeah. No,
Okay.
you cannot just put t equal to 0 here, no? Precisely because if you are integrating over the fields here,
t
you get infinity. No, okay. Yeah, but what you want to do, right? So you want to put this, and then how do you calculate this?
Well, okay, I guess localization has to break down, but it just wasn't obvious how it broke down.
Well, this is like having a coupling constant t, right?
Yeah.
Right? This is just telling you that you
Yeah, no,
should
that's-
be able to compute this at any value of the coupling constant. Actually, I have to say that, for example, the n equal 8, well, this is a bit little, the n equal 8 super-Yang-Mills theory can be computed with localization by essentially cutting into pieces and using the result for localization for each piece of this theory. So that you can still do, and this has been done. For example, people have checked that n equal 8 super-Yang-Mills has the same partition function that ABN theory when k is equal to 1. This you can do with localization.
Okay.